Okay, previously we left off in figure 17.23, which was a motor that was designed to be a capacitor start and a capacitor run motor. Before I go into the section 17.14, which is a permanent capacitor motor, I want to just make certain everybody's clear on this. The capacitor start, the capacitor is going to be shut down by the switch. The capacitor run motor, the part of the motor, the capacitor is going to bypass and be in the circuit all the time, and therefore your phase angles are going to be transitioning between the two different types of motors, whether the switch here is open or closed. When we go into a permanent split capacitor motor, the only thing that's going to change is this rung right here is going to be gone. In the capacitor, the run capacitor will stay in the circuit all the time. So if this is gone, the run capacitor just stays in and fires the start winding and runs the circuit off that, rather than dealing with the switching mechanism and everything in there. So they're in a permanent split capacitor motor here. You will not have any internal switches. You will not have any start capacitors. It will be just one run capacitor. And on the next diagram here in figure 17.24, it's displaying what that run capacitor looks like there. It's upside down, but you notice that it is in a metal canister, indicating that, hey, it'll be in the circuit for a longer period of time. Just like before, though, it will give the motor good running torque in that, because of that added capacitance in there. And again, it goes back to dealing with Eli and the Iceman and how the two correlate with each other on that. So anyway, this is your permanent split capacitor motor, and you can see that that is connected to a squirrel cage fan. So that's not an uncommon motor to have found a lot in the market, but due to our government standards now, we are not usually installing any new equipment with this particular motor anymore. Now you might find it more commonly in other pieces of equipment, maybe a conveyor or something of that sort, or a drill press or those types there. Okay, so before I switch gears here yet again, I just want to recap these commonly used induction motors, AC single phase 110 240 volt induction motors. You can have three main types. You can have actually four. You can have a motor without any capacitors in it, just a standard single phase motor. You can have a capacitor start motor, which is with a switch and a capacitor. You can have a capacitor run motor with just a capacitor in there, and then you can have the combination capacitor start and capacitor run motor. So there's four single phase motors there. Now we're going to go on. We're going to go to a little different style motor. So this is just one more slide here on an open type PSC motor. PSC stands for that permanent split capacitor. Now I'm going to switch. So here's the next one that we're going to discuss. This is our next motor here. This is what they refer to as a multi-speed PSC, permanent split capacitor motor. So yes, it is still a single phase motor. Yes, it can still be run on dual voltage. Yes, in this case, it is running on a 208 to 230 volt voltage rated winding motor here. You can see that it is multiple speed based on the diagram on this other side over here in the bottom. But now we're going to get into the diagrams on this motor. So here's a diagram in figure 17.27. And what we've got here is we've got a PSC motor, permanent split capacitor, meaning there's no switch to engage the capacitor in with the start winding. But the start winding on this, it does stay in the circuit 100% of the time based on the capacitor. There's no switch to kick that out. What is important here with this diagram is the multiple speed. This motor is a 3-speed motor, and what's important is how they do that. What we're doing here is we're going to connect line 1 to our common to our run winding in red, and common to our capacitor and our start winding in the black conductor there. Then all we got to do is we've got to connect line 2 to the desired speed, whether it be high, medium, or low speed on the motor. From there, if say we hooked it to low, it would have the greatest amount of resistance and we would have the greatest amount of voltage drop, and the leftover would be for our in parallel our start winding and our run winding, what's left over. So think about it like this. The highest resistance would give you the slowest speed. Think about that if we're dragging something up a hill, right? The highest resistance is going to take us the longest amount of time to get the block up there. Therefore, if we go to medium speed, we have a little less resistance because we don't have to worry about these windings on the right, and we've only got this on the left. And then finally, high speed, the least amount of resistance to give the run and start winding everything it's got, all the voltage across that. So if it's 110 volts, it's going to have full 110 volts across the start and the run in that particular motor. Something else to keep in mind though, even though that these other speeds are not connected to anything, electricity does flow in all directions. So if we're connected to the high speed, the medium and the low will be energized, so it is very important that you cap those leads with a wire nut of some sort, or put them on what they refer to as the park terminals for them variable speed motors. I shouldn't say variable, multi-speed on that. Let's go on to the next diagram on this. So continuing on with figure 17.28 here, we're still looking at that same motor. It's that same multi-speed permanent capacitor motor there where it stays in the circuit. But now what they've added to this is our constant on feature, which we commonly run into in either electric furnaces, forced air furnaces, or your gas-fired forced air furnaces. If you recall with the switch and the auto to on switch, when that kicks on, it energizes a relay, and then the contacts down here change to an abnormal position. With that relay, we can have multiple speeds connected at a time. So normally closed is usually, not all the time, but usually connected to the lower speed in your furnace, maybe medium as well, but usually it's going to be the lower speed for heating. And then you've got that heat operated, in this case, bimetal switch there, that when the cabinet warms up, it energizes the low speed. If the thermostat was kicked to the on function, the switch was kicked to the on and the fan was designed to run continuously with that feature, then the power would come in and these contacts, these two would go to their abnormal position. The black contact would be closed and the red contact would be open abnormally. So therefore the power would come in and run through the black contact here and engage the high speed, and at which point the low speed would be de-energized. It is important that we only energize one speed at a time, otherwise you can damage that motor as well. Also keep in mind that the medium speed here would still need to be capped because electricity can flow to those other speeds. Here we go, we're switching gears yet again, taking a look at figure 17.29, and what we're looking at here is yet a different type of motor, maybe could be thought of as a specialty motor, but still fairly common. This motor here is what they refer to as a shaded pole motor. If you look at the diagram, you'll notice that it only has one winding and therefore would only be designed to run on a single voltage setup here. That winding, line 1, enters, wraps around the poles accordingly to its needs, and that will create the magnetic field in order to make the rotating rotor in the center rotate. The last thing about the shaded pole is the shaded pole itself, and that's this little copper band that wraps around each one of these quadrants here. Some have 1, some have 4, some have 2, depending on the type of motor and how big it is there. But what that's going to do is it's going to induce voltage from our winding into our secondary winding, and that's going to act to give us the starting force, that starting magnetic field, because of Eli in there, where we'll have that lag time with our voltage in leading the current, or voltage leading the current by 90 degrees. That will give you that phase shift in order to get that rotor rotating inside that shaded pole motor. In order to reverse a shaded pole motor, it's relatively simple. All you got to do is pull the rotor out and reverse it. Put it back in the opposite direction. Some are capable of that and some are not. So you just got to determine that from the manufacturer of the motor and if it has capabilities. Sometimes you even got to unbolt the stator and reverse the stator. So one of the two should be capable of being reversed on most motors. Where you'll find this motor commonly, the most common place that I find it is in a bathroom exhaust fan. We run across quite a few of them up there. Here in figure 17.30, we've got a couple of examples of the shaded pole motors. As I was stating, this one, B and C, would be the most common to see in them bath fan motors. They're relatively small, usually in those fan motors they can probably fit in about the palm of your hand, so they're not real large. But here they're showing how the rotor is removed from the stator, stationary part of the motor, and those shading coils on a couple of these internal in there. So in order to reverse these, you take that rotor out, and in this case you would have to bolt it up to the other side of the stationary part of the motor on that. So don't forget, this little copper bar right here is the shading coil, the shading pole, and you can see it down here on the bottom as well with that. And that's where I'm going to leave you for right now, and then we'll pick back up next. We're going to go into a little more of the three-phase side of things, the three-phase commercial side of different motors that we can run into. So we'll catch you on the next one.